In this worked example, we're going to use the case of a space elevator. Now, if we're going to have a future of the Starship Enterprise zipping around the galaxy colonizing other planets, the most difficult bit is going to be the first 100 kilometers, getting people from the surface of the Earth above the atmosphere. Once you're in space, it's fairly easy to do other things. You can build very fragile spacecraft that don't need to deal with wind resistance. But if we're going to get people that first few 100 kilometers above the atmosphere, it's a huge amount of pollution and expense if you have to do it with rockets. And so there has been a proposal, originally by some science fiction authors, but it's been seriously studied, to build elevators to space. Here's the idea. You've got the Earth, and what you do is you have a space station or an asteroid out at a geostationary orbit. Now, a geostationary orbit is an orbit far enough away that it takes 24 hours to go around the Earth. If the orbit is over the equator of the Earth, so let's say that's the North Pole and the Earth is spinning like that once every 24 hours, if this also goes around once every 24 hours, this satellite or asteroid will appear to hover over one point on the Earth's equator, which means you can lower a cable from it to the Earth's surface, bolt it down at both ends, and then maybe have little cars that drive up and down the cable. And so you really could build an elevator into space. And this has been very seriously studied. It would be by far the cheapest and most efficient way to get things into space if you can build it. You have to have some sort of counterweight out here as well, otherwise the tension on the cable will pull the satellite out of geostationary orbit, but that's all perfectly feasible. The main problem is the tension in this extraordinarily long cable. And that's what we're going to try and calculate in the next few videos. First, we should think about what exactly is a geostationary orbit. Well, for anything to be in an orbit, gravity, the gravitational force, which is g, m of the Earth, m of the spacecraft, whatever, over r squared, has to supply the centripetal force, mv squared over r. So the mass of the object cancels. Now, how far out do you need to be to go around once every 24 hours? Well, the best way to do that calculation, instead of using the velocity v, is to use the angular velocity, which is the change in angle, theta, per unit time. So angular velocity omega equals the rate of change of theta. And the linear velocity here, v, once theta goes from 0 to 2 pi, it'll go a distance of 2 pi r all the way around the circumference of the circle here. So omega has got to be 2 pi over 24 hours, which is 24 times 60 times 60, equals 7.27 by 10 to the minus 5. So that angular speed means you go around once every 24 hours. The linear speed, if you remember, v is just equal to omega r. So we can rearrange this equation. So we get gm over r squared equals v squared, which is omega squared r squared over r. And rearranging that, we find that r cubed equals gm over omega squared. And so r equals the cube root of gm over omega squared. And for the mass of the Earth, which is 5.97 by 10 to the 24, the gravitational constant g is 6.67 by 10 to the minus 11. We've just worked out omega. That comes out as 42,000 kilometers. So a long way up. But if you could put that's distance from the center of the Earth, it's 36,000 kilometers above the Earth's surface. So if you put something up there, 42,000 kilometers up, and you can lower a cable down to the Earth's surface, in principle this could work. But what will the tension be?